Okay, thank you. So I would like also to thank the organizers for this nice conference and for the opportunity to speak here. I will say something on a recent joint work with Jiří Spurný based on this recent preprint. It is devoted to vector valued Choquet theory. Well, some integral representation of for vector valued function spaces is not a new thing. It goes back to 80s, but our aim was to develop some notions of simpliciality, some reasonable notion of simpliciality which was missing. Let me start by recalling the basic setting from the scalar case. In the scalar case, a basic object of interest is a function space. It is a linear subspace of space of continuous functions, real or complex valued. And we are looking for some nice representing measures for functionals. So this is a definition of the set of representing measures. If you have a functional on H, representing measures are those measures who represent the functional via this integral formula and have the same norm as the functional. It means the minimal possible norm. This space is, this set is always non-empty. It is an easy consequence of Hahn, Banach, and Riesz theorems. A particular case of these functionals are evaluation functionals. If evaluation functionals at some point of the compact K, these are denoted by phi h of t. This h, of course, refers to the function space H. And in this case, we have this special notation. The representing measures of point means representing measures of the evaluation function. Let me also point out that in the special case, which is the classical case, if H contains constants, then necessarily representing measures of any point are probability measures. Well, so these are measures, representing measures, but as I said, we are searching for nice representing measures, so-called boundary measures. So let me recall again the definition of Choquet boundary. Choquet boundary of K, of H, say, is the set of those points in T such that the evaluation functional is an extreme point of the unit ball of the dual of H. Let me remark that from the classical case, you may know another definition, which is equivalent if H contains constants and separates points. Then it is the same to say that the only representing measure is the Dirac measure. The Dirac measures are denoted here by epsilon. And further, a measure on K is boundary, H boundary, if the image or push out of its variation under the evaluation mapping is maximal. Maximal in the Choquet ordering. So Choquet ordering, let me recall it, it is on compact convex sets, on positive measures on a compact convex sets, it is ordering via the cone of continuous convex functions. Here, this X is the unit ball, yes. And these measures have some relationship to Choquet boundary. If K is metrizable, then boundary measure is just a measure carried by the Choquet boundary. in this case, the Choquet boundary is G delta. If K is non-metrizable, it is more difficult. And if it doesn't contain constants, it is even more difficult. But I will, this is not my point today. And the known representation theorem is the following. If we have any functional, then it admits a boundary representing measure. The very classical case in the for real valued spaces and containing constants and separating points is the Choquet-Bishop-Deleuze theorem from late 50s. This was later generalized to a complex case. Later, even the assumption of containing constants was relaxed. And in full generality, it follows from result by Saab using some vector value techniques. And this theorem inspires definition of simpliciality. So H is simplicial if any T admits unique boundary representing measure. So uniqueness of representation, and a bit stronger notion, functionally simplicial if the uniqueness holds for any functional, not only for evaluation functions. This functionally simplicial by Fur and Phelps was called some uniqueness. It satisfies uniqueness, so something like that. And this is somehow well studied. Let me now pass to the vector valued case. Here, the setting is analogous. We have a vector valued function space. It is a linear subspace of the space of vector valued continuous functions. On a compact space, vector valued means with values in a real or complex Banach space, and of course with the standard supremum norm. And in this case, we use the following associated scalar function space, H weak. This is the linear span of compositions of elements from H with functionals on E. So this is then scalar function space, which is somehow associated to H. We will see that it plays some non-trivial role. And if we now want to work with some integral representation, there are two natural ways of representing something by measures. The first one, which was used in the literature, is represent functionals on H via integration with respect to vector valued measures on K. Vector valued measures means with values in the dual of E. Or another way is represent operators from H to E via Bochner integration with respect to scalar measures. Well, in the scalar case, both ways coincide. Yes, because in the scalar case, where E is the field, operators and functions are the same. So let me now start with the first case, representing measures of functionals. Then the situation is somehow analogous to the scalar case. If we have any function on H, there is, by Hahn-Banach theorem, we can extend it to the space of continuous functions with preserving the norm, and use Singer's theorem, which is some vector valued version of Riesz theorem, that the dual of CKA is the space of E star valued measures. And the integral is defined, well, this is for very simple functions, and then it is extended by linearity to simple functions, and then by continuity to functions which are uniformly approximated by simple functions, in particular to continuous functions. So this is something classical. And representing measures we can define essentially in the same way. Those measures which represent the function in the via this formula integral and have the same norm. And it is completely analogous to the scalar case that by combination of Hahn, Banach, and Singer theorems, this is always non-empty. Moreover, a representation theorem due to Sabet and Lagrange, there is always a boundary representing measure. Boundary here means that the variation, this is vector measure, whose variation is boundary with respect to this H weak, which is somehow canonical here. Now, let me compare it with the second case. First, for operators, not all operators may be represented by Bochner integral. So we define representable operators as those who can be represented, and define rep norm as infimum of norms of the respective measures. And define the set of representing measures, again, measures who represent, sorry, this should be U, not psi, who represent the operator and have the minimal norm. Well, here at the first sight, it is not clear that the minimum is attained, but it is, because I find interesting that this representing operator, representable operators, are in a one-to-one isometric canonic correspondence with the dual to this scalar function space H weak, such that the representing measures coincide essentially, and evaluation functionals correspond to evaluation operators. Well, this is here, of course, evaluation operator is operator from H to E, evaluation at point T by analogy. So, and via this, we can deduce the following corollary. First, representing operators is the same as representing functionals in the scalar case. Moreover, from the scalar case and this identification, we get that this set of representing measures is non-empty, and hence the infimum in the definition of rep norm is attained. And moreover, another consequence of the scalar case is that there is always a boundary representing measure. Boundary, again, with respect to this H weak. And now, using these two approaches, we can define some notions of simpliciality. First notion is which we call weak simpliciality. It means that for each t, there is a unique representing measure of t. Here, this mt means of the evaluation operator. This is from the second evaluation operator at t, and this is via this Bochner integral. Functionally weakly simplicial if the uniqueness holds for all representable operators. Well, now, functionally vector simplicial if the uniqueness holds for each functionals in this Singer duality. And the presumably easier way is vector simpliciality, just when we require the uniqueness just for these special functionals, which are composition of evaluation operators with functionals on E. And let me remark that due to the characterization, due to identification with the scalar case, H is functionally weakly simplicial or weakly simplicial if and only if H weak has the corresponding scalar property. So this is like that. And it can be also observed that in the scalar case, it means where the Banach space is just a field, then these two ways weak and vector coincide. To analyze simplicity in more detail, already in the scalar case, an important tool is the space of H affine functions. So these are all continuous functions on K, such that for each T and for each representing measure of T, we have this integral equality. Yes, so this is all functions which satisfy this kind of barycentric formula. And in the vector valued case, we have two versions of this. AC weak, which is formula is the same, just we have this Bochner integral and of this evaluation operator. So this is just the same. And AC vector H, it means that we have an analogous formula, but for this special kind of functions, for this composition of evaluation operators with functions on E. Let me remark that in the scalar case, everything coincides. So the weak and vector approach is the same and coincides with the scalar case. Now, let me somehow compare it. First, because this weak, because this correspondence with the scalar case, this AC weak H and weak simplicity are stable under renorming of E. It means because they depend just on the properties of H weak, which is independent of the concrete norm of E. While AC vector, H and vector simplicity may change after renorming of E. So it may change both ways. The space may change, may increase, decrease. Further, H is weakly simplicial if and only if this AC weak is weakly simplicial. This is completely analogous to the scalar case. While for vector simplicity, we have only one implication. This one, which is somehow easy, and the non-trivial one fails. These two things, AC weak and AC vector, are incomparable in general. So no inclusion in general. And vector simplicity and weak simplicity are also incomparable in general. However, if we add the assumption that H separates points and contains constants, these constants are important, then the situation is much easier because then this AC vector is contained in AC weak and vector simplicity is stronger, in general strictly stronger than weak simplicity. And we have the following theorem, which is some analog of such a classical theorem in the scalar case for scalar spaces separating points and containing constants, that H is vector simplicial if and only if this AC vector is vector simplicial, if and only if it is functional vector simplicial, and if and only if it is weakly simplicial, and these two sets of affine functions coincide. And the last thing, which here may look a bit artificial, but it is in fact natural. This is something stronger than the stronger version of uniqueness. The only H boundary measure which annihilates this AC vector is 0. So this is a complete analog, essentially complete analog to the scalar case. Okay, so thank you very much.